Okay, so we've got this column here. It's fixed on both ends, so there's no rotation happening at either the top or the bottom. And we got the midpoint, so it's braced in a manner that prevents it from displacing in the x direction. Uh, the particular column is an S88 by 23 section. Don't bother trying to look that up in Hibbler's because I didn't get this from Hibbler. There's another type of uh, type of I-beam that isn't listed in your textbook, but I got the values available. So it's gonna be made out of steel, and we're trying to figure out what the critical axial load is. So again, just looking up the values for the IX and the IY, kind of based upon this orientation. We got IX is 64.7 inches to the fourth. So again, that's resisting rotation, but that IY is going to be 4.27 inches to the fourth, and that's resisting rotation about this way. So not surprising looking at this thing. It's you know fairly easy to tell that it's designed to resist rotation about the x-axis a lot more than it is about the y-axis. So the cables prevent displacement in the x-axis, so that such displacement would be occurring when the rotate like when the bending that's occurring is about the y-axis. I want to figure out what the critical load is. So again, in general, critical load is pi squared EI over the effective length squared. But there's a hitch in this one, so we'll talk about that. So the one failure mode that's fairly simple: rotation about the x-axis. That one's just fixed. The cables don't come into play because it's not going to be because the rotation about the x-axis is going to cause displacement in the y-axis. So that's just a column that's fixed on both ends. So the effective length there is just half the half the length. So if we got that'd be equal. It's it's a 24 foot long beam overall. So half that effective length is 12 feet, or 144 inches is going to be its effective length. Now, if we're rotating about the y-axis, we got this hitch here. So it's not going to be allowed to displace at the center. So it can still rotate there, so no displacement. So that is basically equivalent to if you had two columns, one which was each of them was fixed at one end and then pinned at the center, and there's rotation allowed, free rotation allowed in the center there. So that essentially means that we can kind of use the effective length of one of these imaginary half beams to do our calculation. So the K value for a pinned for a beam a column that is pinned at one end and fixed at the other end is 0.7. So the effective length that we'd use would be 0.35 of the overall length. So 0.35 times the 24 feet, that gives us 100.8 inches. So now we know everything else we need, so we just got to plug them into our equations. So our critical loads, pi times EI over L effective. I forgot to throw the square there. I don't know why. Yeah, anyways. Over the L effective squared. So 3.1415 squared times 29 times 10 to the 6 pounds per inch squared times 64.7 inches to the fourth. divided by 144 inches squared gives us a value of 843 kips. So pretty hefty load it's able to carry. But the with rotation about the y-axis, however, again that thing's uh, not able to resist rotation about the y-axis nearly as well. Its I is a lot lower. So I got the 3.1415 squared times 29 times 10 to the 6 pounds per inch squared times 4.27 inches to the fourth divided by 100.8 inches squared. So that gives us a value of 120.3 kips. So the cable thing certainly helped. Essentially, what we're able to do, because otherwise, essentially, we'd be using the same values here, except for the effective length. If we hadn't done the cable thing, then we'd be using then it'd still be then we'd be using a fixed connection on both ends, but an effective length of the 144. So essentially, due to the fact that we're due to the fact that they use the cables to prevent the rotation, we're dividing this value by a smaller number than we would have if we were if they hadn't used the cable. So it would have been even smaller if we hadn't used the cable. But yeah, that's about that.